Uh, Good afternoon, everyone. So this session I am going to take on unsupervised domain adaptation. Am I audible?
Yes.
Okay, thank you. Okay, so I think no need of introduction. So already I have been introduced many times and I have already given lectures. Okay, so now directly I'm going to present my screen and start the session. Is my screen visible? Hello.
Yes.
Okay, thank you very much. Okay, so today we are going to talk about unsupervised domain adaptation for image classification, and we will take some application of remote sensing as well. So some data sets of the remote sensing which we have considered for the research purpose, that also I'm going to show to you. Okay, so what is basically the domain adaptation? So domain adaptation is basically the sub part of transfer learning. Okay, so earlier I also talked about basically what is the transfer learning. So transfer learning is so when you know the C++ language, right? And when you are going to learn some other language such as Python, so it will be very easy for you to learn Python language, because some of the concept, right, in both C++ and Python, which are common, right? So those concepts which are common, so again, you need not to learn in the Python. So here, so the knowledge which is available in one domain, C++ domain, right? Then you are going to automatically transfer into the Python domain, right? So only some syntax may be changed, right? So here also somehow you are performing the domain adaptation kind of task. So similarly, if we talk about, mathematics, if you are very good in maths, if you are very good in, linear algebra, if you are good in, probability, right? And when you start learning machine learning languages, so it will be very easy for you to adopt the concept of the machine learning, because some of the concept, right? So they are like, fundamental, and they are baseline for learning the machine learning languages. So again, here automatically you are transferring the knowledge from maths to the machine learning, right? So here, so somehow from one domain you are transferring the knowledge to another domain. So that is basically the domain adaptation. Okay, so to understand it, what is specifically the domain adaptation and what kind of problem of the domain adaptations can be solved. So let me take an example here. Okay, so right? So here, so you are given some images which are taken from the DSLR camera images, and you are also given some images which are taken from the webcam camera images. So as you know, right, two objects are there. One is keyboard, another one is the headphone, right? So these images are basically the labeled images. Okay, so you would like to, train the classifier, right? So let us say that you have some classifier or some neural network model, right? So some model is there, ML model. So you have a DSLR camera images So DSLR camera images, right? What kind of images are available? So as you can see, like keyboard and headphone. So these images are available. And one more thing, these images are labeled images, right? So labeled images means definitely you are one hot encoding, dummy coding. So let's say if keyboard is there, so you are going to represent it by 0, right? And if it is a headphone is there, then you are going to represent it by 1. So with the help of this label data of DSLR camera images, right, you can train this machine learning model. Okay, after training this machine learning model, right, so what basically you want, so if you test the images which are taken from the DSLR camera images, then the performance of this, you know uh, this classifier or machine learning model would be very good, right? But what if the images, right, which are taken from the webcam camera images? So these are the webcam camera images. Okay, so let's say here again some keyboard and headphone. The images are, but the thing is these images are not labeled images. And if you give these images to the classifier which is trained on the DSLR camera images, then the performance of this model may be poor. So if I ask you, so what is the reason? Because since the objective of this particular machine learning or and deep learning model is to classify two objects only, right? What are those two objects? Like keyboard and headphone. So if at the time of testing, if you give the images from the DSLR camera images, then the performance of this model is very good. But why? Because since the objective of this classifier is to classify only keyboard and headphone, right? But if you are giving the images are taken from the webcam camera images, then why this model is performing poor? So can anybody tell me what is the reason why this particular classifier is giving poor performance when you are giving the images from the webcam camera images? What is the reason? Any one of you?
Because it's trained only with the DSLR images.
Yes. But the objective of this classifier to classify only like keyboard and headphone, right? But same classes you are giving, but why it is performing poor on the webcam camera images? What may be the reason? Yeah. So yeah, Kunti, yeah, this is the very correct answer. The variations and the quality of the images. So as you already know, right? So see, the DSLR camera images quality is very good, right? Compared to the webcam camera images. So because of that only this quality, okay. So the performance that this trend classifier from the DSLR camera images is not performing well on the webcam camera images. Okay, if you try to visualize like DSLR camera images in some 2D space, okay, so maybe you may use some dimension reduction techniques such as principal component analysis, TSNE, right? Which basically what it try to do, it try to map, right, high dimensional data into some 2D space. So let's say if the some 1 minute. Someone can you please? It is a noise. It is giving. Unmute out yourself. Okay. So now, so when you plot some high dimensional images such as keyboard in some space like 2D space, if you try to visualize, so let's say these high quality images, the keyboard come in this particular point. Okay, so similarly, if you try to plot some keyboard images which is taken from the webcam camera images, and if you try to plot, so it may come somewhere here. Okay, because this is also the keyboard and this is also the keyboard, but the plotting, right? So the point, right? So basically this is from this images is, you can visualize it. This is the web DSLR camera images and this is the webcam camera images, right? If you try to take the same images from the DSLR camera images, one more images, and if you visualize, so somewhat it will come here again. Okay, and again, if you take the images of the keyboard from the DSLR camera images, and if you try to plot, so somehow they will come very near to this particular space. Okay, similarly, if you take the images from the webcam camera images and if you plot, so they will come somewhat here. Okay, so you can see the object, they are same, right? If the objects are same, then if you take many images and if you try to plot and if you try to visualize in some 2D space, the distance between them should be less, right? But here you can see, even though they are the same class, what is the same class? Keyboard class, but due to the quality of the images, they are lying very far. As you can see here, they are lying very far. Okay, so the distance, the same keyboard here, the distance you can see this much. So this distance, why this distance is coming? Because of the quality. Okay, so because one image is lying here, so this image is taken from the DSLR camera image, and this image is taken from the webcam camera images. Okay, actually, please unmute yourself.
हम फिल्टर अगर बता दीजिएगा तो फिल्टर हम डायरेक्ट परचेज कर लेंगे, वीडियो तक नहीं जाना है, डायरेक्ट प्रोक्योरमेंट होगा। हाँ हाँ, तो वो कुछ है आपके पास?
Sir, you can mute everyone, no?
Yeah, that is, I'm just checking.
अच्छा, कल कितने बजे तक आ जाएगा?
How to mute them? Can anybody suggest me?
कर देते हैं। अच्छा, वही कहा कंप्लीट, इसीलिए मैं परेशान था कि
Okay, so now as I told to you, right? So this image keyboard images you had taken from the DSLR camera images, and these images you have taken from the webcam camera images, right? Even though they belong to the same class, that is keyboard, but due to the quality, okay, so they are far apart. So can you see they are far apart? Because since if they belong to the same class, okay, so then the distance between the same class images should be less, but this much distance distribution or the distance is coming. Okay, so this distance is coming because of the quality of the images. Means this is a high quality camera images and this is the low quality camera images. Because of that, they are lying far apart. Whatever the distance and this distance is there. Okay, so this distance we call it as a distribution gap. Okay, so this distance we call it as a distribution gap, or we can also sometimes we can call it as a divergence. Okay, so basically the objective of the domain adaptation approaches is to minimize this distribution gap. Okay, so domain adaptation approaches project this data. Okay, initially they are lying in this particular space, so they will project in such a space where, so these samples, right, so they are far apart, even though they belong to the same class, but due to the quality of the different quality of the images, they are lying far apart. Okay, so by transforming them by using the domain adaptation or transfer learning technique, we will project in such a space the distance between the similar class sample will come close. Okay, so that is basically the goal of the domain adaptation approaches. Okay, so I hope now the domain adaptation is clear, and what is the distribution gap, okay, and what is the divergence, okay, so and why this divergence is coming. Okay, so I hope this thing is clear. Okay, so because of that, only the performance when you test it on this webcam camera images, then the performance of the model is poor. But if you take the images from the DSLR camera images, then the performance of the model would be good, because there would not be divergence between the images, because since they are taken from the same camera images, so definitely the images will lie very close. Okay, so what is the problem? So still, if you want that the performance of the model should be good on the webcam camera images, then you can say that why not, sir, you can train the classifier by using the webcam camera images. Yes, you can do it, but what we will have to do? Again, all the webcam camera images, you have to label it manually, right? You know, right? Without label, you cannot train the supervised machine learning algorithm, right? So you require the label information and labeling the information. So if you are having, okay, 10, 20, 30 images, then it is okay. But what about if you are having more than 1 lakh, 10 lakh, 50 lakh, some images, right? Then manual labeling is not possible. Okay, so that's why then the concept of this domain adaptation and transfer learning comes into the picture. Basically, without labeling the target domain, okay, so still you can improve the performance of the model. Usually here, this source domain, the domain for which the label information is all available, we call it as a source domain images, and the target domain which does not contain any label information but unlabeled data they contain, so this domain is called as the target domain. Okay, so here, so now what I have done, so here basically the different symbols, remember different symbols, like here, so circle is representing the source domain and plus is representing the target domain, and different colors like red is representing the keyboard class and black is representing the headphone class. Okay, so what I have done, so these images I have taken, and then I have, with the help of the Disney, I have plotted these two classes into 2 dimensions. So here you can see, so these symbols, okay, so this rounds, this circle of the red color means they are basically the source domain keyboard class, and this is the source domain headphone class, right? I have plotted, I have visualized them in the 2D space. So here you can see, right? So how, like, since all these samples, can you see, they are basically the DSLR camera images and keyboard class, right? So this is also the source domain images, but the headphone class, right? And they all the samples you can say they are very close here, right? So as you know, right? So these, as I told you, right, source domain, the label informations are available. So with the help of the label information, you can draw the decision boundary, right? So here you can see I have drawn this particular decision boundary and I am calling it as a V, right? So usually all the like machine learning algorithm which you have seen, such as support vector machine, uh, k nearest neighbor classification, okay, so they somehow, like, how basically they recognize, how basically they will tell that this sample, if you give some unlabeled sample, and then it will classify to to some particular class, how basically they do it? So basically all the machine learning algorithm, they basically try to draw some kind of hyperplane. So as you can see, so with the help of this label information, now this hyperplane is drawn for the by the source domain classifier. Okay, so with the maximum margin. So here you can see that this hyperplane is drawn to discriminate the keyboard as well as the headphone of the source domain classes. Okay, at the same time, if you try to plot the target domain samples, right, which are denoted by the plus symbol, so they will come somehow here. Okay, so here you can see. So why this much? So even though I told, right, so this red color means they belong to the basically the same class. So this is also the basically the keyboard, this is also the keyboard class, right? But you can see, right, so this much is the distance. Can you see here when I have plotted, right? Because why this distance is coming? Because the origin of both the samples are different. Okay, so these images are taken from the DSLR and these images are taken from the webcam camera images. Okay, so similarly here also the headphones, so these are the source domain and these are the basically the target domain. Okay, so now with the help, because see what is the assumption here, the target domain you don't have a label information, then how you can draw this hyperplane which can discriminate the target domain samples? Means like this plus of red color and the plus of black color, right? So because you don't have the label information, so you cannot train the classifier. But what you can do, why not you can utilize the hyperplane drawn by the source domain classifier. Okay, so let us see if you try to utilize the hyperplane drawn by the DSLR and source domain classifier. So this is the V is the hyperplane, right? So I have drawn and I am going to discriminate the target domain samples. Okay, so now you can see all the plus samples are being with the help of this hyperplane, all the plus samples, they are being correctly classified. But some of the samples, can you see here? So these samples, so just I have drawn the one circle here and over the symbols, they are also being misclassified here. Okay, so some samples are correctly classified, all the plus samples, but these samples are being misclassified. Okay, so that is basically due to the distribution gap. So even though you are trying to utilize the hyperplane drawn by the source domain classifier, may not be efficiently utilized to discriminate the target domain samples. Like some of the samples of like this plus class of the target domain means headphone, they are being misclassified the hyperplane drawn by the source domain classifier. Okay, so then what you can do? Okay, so you can use the domain adaptation approaches or transfer learning approaches. So project the data in such a space. So now I have projected some concept of the domain adaptation. Now you can see the distribution. So here you see there was some distribution gap, right? The differences was there. So I have minimized. So now after projecting, so the distribution has been reduced. And here also you can see the distribution has been reduced. Now the same classifier, okay, which you have drawn by using the source domain label data, now can be utilized effectively to discriminate the plus symbol of the target domain as well. So here you can see, right? So this is basically the domain adaptation and different techniques are there. So okay, so one by one, so I am going to tell you so how basically this domain adaptation come into the picture. Okay, and then so what research works we have done and what approaches basically we have done, right? So some of the papers I would like to discuss with you. I hope now it is clear to you what is domain adaptation and what basically the domain adaptation is going to do. Okay, so now here also what I have done, so I have taken the of Office Caltech data set. Okay, so in that particular data set, basically, there are 10 classes are there. Okay, so here, basically, the different symbols are representing basically the different. Here, the different symbols like plus symbols, they are representing the source domain, and the circle symbols are representing the target domain. And there are total 10 classes, 1 to 10 on the source domain. So here you can see, okay, and in the target domain also, here you can see. So symbols are there. So I have plotted the initial visualization, initial representation of the data. So you can see like how different classes they are residing in the original space. So with the help of the Disney, I have plotted into the 2D space. So now you can see if this kind of data, if you are going to give to any classifier, conventional classifier or machine learning algorithm or deep learning algorithm, so even like for you, right? So if I ask you to draw the decision boundary which can discriminate the different class symbols, so it will be difficult for you also, right? If this kind of data, if you give to classifier, right? So then you can see, so the symbols, right? So these many symbol data are being misclassified. So I have just the samples which are being misclassified, right? I have drawn the circle over there, over them. Okay. So, but if you use the machine learning algorithm, sorry, if you use the domain adaptation approaches, so it will project, okay, in some space. So here you can see, so this is the learned representation. You can see, right, after the learned representation, if they belong to the same class, then the distance between them will be reduced irrespective of whatever the domain is. So here you can see, so the well separated cluster you have got, right? Even if I ask you to differentiate the different classes, to discriminate the different classes, it will be very easy for you, right? So how basically you can discriminate? So separate hyperplane or decision boundary you can draw, and you can discriminate the samples here, right? So it will be easy for you. So same thing. So this is basically the after, this is before the domain adaptation, and this is after the domain adaptation. So this real examples I have taken, I have visualized it, and then after applying the domain adaptation approaches, now again I have visualized it. So definitely after adaptation, right, the performance of the model will improve. Okay. Okay, so like domain adaptation approaches basically could be categorized into the two types, right? One is the semi-supervised domain adaptation, and another one is the unsupervised domain adaptation. So in the case of unsemi-supervised domain adaptation, so in the source domain, you have fully labeled data. Remember, in the source domain, you have a fully labeled data. Okay, but in the case of the target domain, you have partial labeled data. Means you will not have the completely labeled data. So some classes may be labeled. Okay, but at the time of testing, you would have the unlabeled data. Okay, so this you can classify it as a semi-supervised domain adaptation or transfer learning approaches. So similarly, in the case of unsupervised domain adaptation, in the source domain, you have a fully labeled data, but in the case of the target domain, you don't have any single labeled data. Okay, you don't have any single label data in the target domain. Okay, source and target I have already given to you. Source means like the images are taken from the DSLR camera images, and the target domain means you have taken the images from the webcam camera images. Okay, so this setting or this the data, if you have this kind of scenario, so then you can develop the unsupervised domain adaptation approaches. And if you have the data like this, then you can develop the semi-supervised domain adaptation approaches. Okay, so now I have just given you the overview of what is basically the domain adaptation approaches and what are the categories of the domain adaptation approaches like semi-supervised, unsupervised approaches. Okay, so now as I told, right, so you have to develop some project. So how basically you can approach the project and how you can develop the project, how basically you can identify the correct problem, and then identify the what work basically have been done and that particular problem. Okay, and what kind of techniques you can develop. Okay, so just I am going to give you some steps. Just 1 minute. Hello. Yes. Okay, so steps in TL based on the domain adaptation approach, domain adaptation project. Okay, so basically first you have to identify the problem. Okay, so you have to correctly identify the source domain, correctly identify the target domain, and what kind of gaps are there, and what is basically the objective, whether you would like to classify the some images or recognize the images, or you have a task of segmentations, right? So if I tell you, right, so let's say you are going to develop some autonomous vehicle, right? So you have collected the data in the night time, right? So in the night time you have collected the data and you have trained the model, right? Autonomous vehicle. So then definitely if it runs in the night time, if you drive it in the night time, then it will be easy for it, right? It can correctly classify the object. But what if it comes in the daytime, right? So in that case, the model which you have trained on the nighttime object may not work well on the daytime objects, right? Or suddenly, let's say some occlusion come and weather come, some so some other situation comes. So at that time, you may not be the algorithm may not work perfectly. So you have to clearly identify what is basically your source, what is basically the target domain, what is the gap. Okay, so first you have to do all those things. Then you have to identify, right, whether you have label data available, and if you have partial label available. So based on the availability of the label data, so you have to correctly identify which algorithm you would like to develop. Okay, so let's say I identify that, okay, my problem is semi-supervised, so I will read the paper related to the semi-supervised only. And if say my problem is related to unsupervised algorithm, so I am going to choose the unsupervised algorithm only, right? So then after problem definition, defining the problem, you will go to the literature survey. So review some existing domain adaptation techniques. Okay, it may be related to statistical learning, right? And some of the statistical learning I am also going to tell you, right? So I have done quite a lot of work on that statistical learning, statistical domain adaptation approaches, then adversarial learning and contrastive learning. Okay, so related to what works basically, by reading all those papers, you would be knowing what work have already been done, right? So let's say because after reading the work, you will be knowing how much work have already been done. If you don't read the paper, if you suddenly start working on that particular problem, it might be possible that the problem which you are solving, that has already been solved by someone, right? So then whatever work you have done, that would be wasted. So definitely you have to read some papers. Okay, then also once when you are going to develop the algorithm, right? So definitely to show the performance of that particular algorithm, so you have to compare it, right? So for comparing the performance of your algorithm, so you require some data set. So you have to identify, so someone has given some data set and shown some performance. Okay, so you have to identify some relevant data sets, evaluation protocol, and benchmark result. Okay, so then only you can compare the performance of your developed algorithm with the existing algorithm on benchmark data set. Okay, so this task also you have to do. Okay, so then after that data collection, so let's say you have taken some new problem, right? So daytime images and nighttime images, right? That is a different problem. Okay, so sometimes also you have to collect the database. Okay, so data set also you have to collect if your problem is very new. Okay, and somehow related to your problem, it is already there, so you can also test on that particular data set as well. Okay, So then another one is, once if you have collected the data, so you have to apply some pre-processing techniques, somehow resizing the images, normalizing the images. If you have a very less images, so you can also use some augmentation techniques, some like image cropping, rotating, and generate the images with different illusion. Okay, so that work can also be done. Okay, so after these approaches, now the next approach is model design and method development. Okay, so now this is basically the core part. So what you can do, either, because see, now if we talk about the deep learning, right? So deep learning usually like some feature extraction. So now with the help of some uh, convolution neural network or transformer nowadays, like vision transformer, they have become quite popular, so they can extract like global and local features, right? So you have to, because since we are talking about the computer vision, so definitely we have to extract the features, right? So as you know, right, with the help of the convolution neural network, so you can extract the local information, right? But you may not be able to extract the global information, right? But with the help of the vision transformer model, so you can extract the global information as well as, right? So you have to choose which model you have to apply for extracting the features. Okay, so that also, or you may also modify, and you may also come up with a new architecture, right? So those works you can basically do. So you can, so here also the improvement, you can come up with your own new architecture similar to ResNet, VIT, VGG 16, ResNet. Okay, similar to those models. And another contribution you can do is you can propose a new loss functions, right? So far, like you have been using, considering only one loss function for training the model. So what you have been doing, basically, this is your model, CNN model is there, right? And you are feeding the data, some images you are feeding, like let's say access images you are giving, and along with the labels you are giving. And then there is some cross entropy loss function is there, right? So it just required the extracted feature access dash, and then this y, and with the help of this cross entropy loss functions, you are going to train this convolution neural network model. Okay, so that is okay. If supervised learning is there, then fine, so you can use it. But what about, like, you have a two different domain, right? So let's say target domain is there, or multimodal, like you have more than 1, 2, 3 domain also is there, right? So then, so this may not work, right? So in this case, more loss functions you can add. So some domain adaptation loss function, like such as first one is the uh, like first order movement, MMD, okay, and choral covariance matching, okay, LMMD, some entropy, some contrastive loss. So more and more loss you can add. Okay, so that could also be the one more contribution. So here also you can modify, and here also you can modify. So this is the area where you can do some kind of contribution, and you can modify. Okay, and if your modification or your contribution is giving the better result, so definitely that would be your novel work. Okay, so new loss function, new architecture. Okay, you may apply more alignment strategies like statistical, geometrical, and teacher learning. Okay, so now done. Now you have developed you have considered some existing VIT model, and you have come up with some novel loss function. Okay, along with the classification loss. Okay, so some more 2, 3 losses you have added. Okay, now this is done. Now then, what is the next step then? The next step is, so train on the source domain and adopt to the target domain. Okay, then how you can say that it is adopting? I am also going to show you like some source domain accuracy you check, and target domain accuracy you can also check. Okay, so how basically, so you will see that source domain accuracy, for the source domain, like you are testing the data, right? So definitely the performance is very high, like you may reach around 99 or 100% something. But same if you are testing on the target domain, so you will hardly find that 88 or 85 or 90% you are reaching it here. Okay, so then you have to train and you have to evaluate the performance of your model which you have developed. Okay, so now to know, right? So I told, right, this is the cross entropy loss functions along with some one and two more loss functions you are adding, whether like the addition is significant or not. So how you would be knowing, okay, whether the added loss are not redundant, okay, or like the some VIT model is there, some architectures you have modified, whether the modified architecture is really contributing something or not. If it is contributing, so definitely the performance of the model will improve. If it is not contributing, so that definitely the performance of the model will decrease or maybe may remain unchanged, right? So that's why you perform the ablation study. Ablation study means, so like skip any one of the added, like your added objective function or loss function and you see the performance, right? If you find that the performance remain unchanged, then this is the redundant. If the performance is decreasing, right, so then you can say that yeah, it has significant impact on the performance of the model. And then sensitivity studies, like so like if you are going to add some other objective function, so how much contribution you would like to add on the model. Okay, so with the help of some hyperparameter lambda1, lambda2, you may add. So different value you may take. So these value like 0.1, 0.01, right, and 0.01. So on which value they are going to work well. Okay, so that is basically, you can call it as a parameter sensitivity test. So that work you can also do. Another one is the deployment and validation. So after doing all those work, right, so then finally you can deploy your model on the real world target domain. Okay, and then monitor draft performance, how it is basically the behaving. Okay, and you measure the accuracy, right? So that you can also do. Then you can also visualize with the help of the Disney how what basically after applying your domain adaptation approaches, what is the representation of the data. So that kind of work can also be done. Okay, then finally you can document the methodology. What is your methodology, then what data sets you have used, and what are the significant result which you have got, and what is still, if you find that what is the weaknesses and still the area of improvement of your algorithm. So those things also you can measure. Okay, so these steps, basically whatever the 8 step I have just briefed you, so that basically you can use when you are going to develop your algorithm, or when you are going to work on your capstone project. Okay, so that is the way you can also do it. Okay, so now some project direction, right? So where you can work. So honestly, I'm going to tell you that this domain adaptation and transfer learning approaches are being used in each and every sector. Okay, so some of them I am going to just highlight to you, but day-to-day life also you have been using, right? In many places you have been using, right? So now first we can say cross agriculture domain and remote sensing. So cross crop disease classifications. Okay, I'm just going to take a very simple example here. So let us say that you have a potato leaf, okay, and so some leaves are there, some leaves are healthy leaves, some leaves are with the infected leaf, okay, with some disease. So these leaves of the potato are available, right? So let's say you have trained the model from this leaf, okay, healthy and the infected. Okay, so definitely once the model is trained, okay, so at the time of testing, the potato leaf should come. Then the performance of the model would be good. But what about like same kind of disease is there in the tomato leaf? Okay, the disease will remain same, right? Whether it is on potato leaf or tomato leaf, right? But what if the leaf of the infected leaf of the tomato comes? Then in that time, the model which you have trained by using the potato leaf, infected or healthy, may not perform well on the tomato leaf. Okay, so again, if you would like to recognize that tomato leaf infected or not. So then again, what you will have to do, you have to collect the data, you have to manually label it and train the model, and then only you can do. But that is also, again, I told you, right? That is basically the very hectic task. Okay, so then what you can do, then definitely you can use this domain adaptation and transfer learning approaches. Okay, so another example is like wildfire susceptibility estimation, right? So means, let's say if I say, let's say we are in the Madhya Pradesh, right? So Madhya Pradesh region, some weather data we have collected, okay, and we have labeled it and we have trained the model, right? If this trained model, if I am going to give the field of some other state, let's say Delhi, so the Delhi weather data parameter which you are taking for predicting whether today is going to be rain or not, so at that time the model may not behave good. Okay, so then definitely you have to use the concept of the domain adaptation or transfer learning approaches to the data which you have collected from the Madhya Pradesh region should also work for the Delhi region. Okay, so that is also the another area. Another is yield prediction. Okay, so let's say you would like to estimate the yield, right? So what you will have to do, so you have to collect the data from different sources. So sometimes you can take the data of that particular region from Sentinel, like MODIS, okay, and hyperspectral, like through your drone camera, right? So that data you can collect. Okay, so and because see that all the data may have the different distributions, right? So by using the domain adaptation, further you can reduce the distribution gap, and then you can improve the performance of the yield prediction of your model. Okay, so that is also one area where you can use this domain adaptation. Similarly, medical images, let's say you have MRI images of the same disease, okay, and you have the CT scan images, right? So if you train the model from MRI, right, so then it expects that the image should come from the MRI. But what about the CT scan come? So in that case, the model may not behave. So here also you can apply some domain adaptation technique, like cross hospital histopathology classification also. So some big organization, right? So they have collected the data, they have given, right? They have a very good resources, like public hospital, like they have a big machines, right? Very costly machine. So they have also produced the data, right? But let's say some hospital, like local hospital is there, he doesn't have that much big machine for taking the some data, right? So in that case, what will happen? So then the directly you may not apply that public data, right? So then you have to again apply the this domain adoption technique here. So domain adaptation for Alzheimer prediction also. So this is also data set is there, local scans are there, right? So you consider this local scan as a target domain, this is as a source domain, and you apply some domain adaptation approaches, like then you can see that the performance of the Alzheimer predictions can also be improved with the help of the domain adaptation. Okay, so these are the areas. Another one is like autonomous system robotics, right? Simulation to real adaptation for object detection, right? So sometimes what happens, so they basically try to do some simulation, okay, by using some tools of Unity and Gazebo, right? So train the model on this simulation and adopt to the real world camera feeds. Okay, for that purpose also you have to use the domain adaptation approaches. Similarly, adopting the perception models across cities, like some you use some kitty data set, source domain, right? So this is basically the some video game or some data set is available, okay, and then you are performing it well on the some real street data set. For that purpose also you can use the some domain adaptation approaches. Similarly, some industry and surveillance, right? So train on some high resolution images and test on some CCTV camera images, right? For that purpose also you can use. And product defect detection, source domain you may consider as a synthetic data, right? And target as a real production in the line images. So if I take an example, let's say you know, right? So underwater animal images. Okay, so that example I'm going to tell you after some time. Just wait for it. Okay, so now like domain adaptation approaches. So what are the categories of the basically the domain adaptation approaches? So domain adaptation approaches could be basically categorized into two types. One is shallow domain adaptation approaches, and another one is the deep domain adaptation approaches. Okay, so shallow means, what is the meaning of the shallow? So shallow domain adaptation approaches basically relies on manually crafted or shallow features, such as like in the morning also Prantik Sen he told, right? So before before the deep learning model uh, came into the picture, right? So there was some techniques like HOG and shift. Like by using these techniques, we used to extract the features for the machine learning algorithm, such as support vector machine, k nearest classification, right? So this technique basically relies on this kind of feature extraction method. Okay, then manually feature engineering is usually required, right? There is some particular person who will manipulate the features as per the requirement of the classification model. Okay, and these shallow domain adaptation approaches usually uses some traditional classification algorithms such as k nearest neighbor algorithm, support vector machine, logistic regression. Okay, and this kind of approaches are typically applied in smaller scale or similar task, right? On the real task, hardly you may apply this kind of algorithm. Okay, so like real task means like autonomous driving car, right? So in that autonomous driving car, you may never be using this kind of algorithm. Okay, and this manual features. Okay, and this manual feature engineering and traditional algorithm, nearest neighbor and support vector machine algorithm. So in this case, right, so definitely you will go for the deep learning algorithm. Okay, so coming to the deep domain adaptation approaches, so utilizes deep features extracted by the deep neural network, right? So definitely if image is there, right, so then you feed it to the some model, like it may be CNN, and those features basically you extract and then you give it to the some classification like a cross entropy or some kind of model. Okay, so here feature engineering is automatic, no manual intervention, like no person is required, automatically it learn from the data. But in the case of shallow domain adaptation approaches, before giving to the model, there would be some person. Okay, manual engineering is required. So often uses end-to-end learning with software classifier or domain adversarial training. So here I told, right, so no person is required. In between, automatically just you fix it. So from automatically it extract the feature and train the model of the CNN here. And definitely it is suitable for large and complex data sets. Okay. Okay, now coming to the shallow domain adaptation approaches. What are those approaches available? Okay, so shallow domain. It is not necessary that you have to use all the time the deep domain adaptation approaches or deep learning approaches. So there are some algorithms also available. Like, so those algorithms we call them as a shallow domain adaptation approaches. So they don't uses deep features, right? Directly. Okay, still the performance of the model can be improved. So first approach is transfer component analysis. Okay, so basically what basically this transfer component analysis does, so this transfer component analysis try to reduce the marginal distribution of the source and target domain. Okay, so if I take an example, what basically this transfer component analysis is doing, so here let's say you have a two class. Okay, so I'm just going to denote two class plus class and the minus class. Okay, so this is basically you are calling it as a source domain. Okay, you have another data also, the source domain, and this is the plus class. and the minus class. And this is the target domain. Okay, so you are denoting it by a T. Okay, so what basically transfer component analysis does, so it try to find out the mean of the source domain. So can anybody tell me, when you for finding out the mean of the source domain, do we require the level information? Do we need the level information in order to find out the mean of the source domain? Can anybody tell me? Do we need the level information of the source domain? No. Yes. We don't require the level information of the source domain. So simply, right, the data is available, right? So with respect to the dimension, you can easily point. So the mean point may come here, somewhere here. Okay. So similarly, for the target domain as well, you can find the mean somewhere here. Okay, and then what basically this transfer component analysis is do, it try to reduce the distance. So this is the distance, right? The distribution gap. So with respect to this mean, so they try to reduce the distribution gap between the source and the target, right? So if you reduce this distribution, so then you project in some other space like phi, right? Where you see this plus plus plus. If you reduce the distance, okay, so then this plus plus of this one also, target domain, if you reduce the distance, and this is somewhere here. Okay, so now you see what has happened here. Okay, in the new distribution, after minimizing the marginal distribution of the source and the target domain, both the domain, they have come very close. Now, with the help of whatever the hyperplane which you can learn from the source domain can be utilized to correctly discriminate the target domain sample here. Okay, so that can be done. Okay, so this is basically, you call it as a minimizing the marginal distribution. So this is done by using the transfer component analysis. That is the first paper. Okay, so Pan et al. Proposed it in 2011. Okay, so this particular paper. Okay, so now you can say, right, so this is okay, but what if the data are like this? So if the data is distributed, so definitely this transfer component analysis will work perfectly. So some of you may ask, sir, what if the data is distributed like this, plus plus plus, minus minus minus, right, and plus plus plus, sorry, minus minus minus, and plus plus plus. So the mean is here and the mean is here. Okay, and then definitely if you apply the this is the source target, this is the target domain, and this is the source domain. Okay, if you apply the marginal distribution, minimize the marginal distribution, so they will come in some space, right, where you can see plus plus plus, minus 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 minus, right, and then here also the plus plus plus, sorry, here the minus minus minus, plus plus plus. So you can see, if you try to minimize, if the data is distributed like this, source and target domain, so all the plus symbols are collapsed with the minus symbol, right? So definitely the performance may be very poor, isn't it? So then what you can do, so you can use, like, along with the marginal distribution, you can also consider the conditional distribution. So this joint Long et al., this joint distribution adaptation Long et al., they found the limitation in this transfer component analysis, and then they come up with the new solution. Okay, so what was the solution basically? So means aligning the marginal distribution is okay, but you have to also take care about the conditional distribution as well. Okay, so what they told, so why not you also find out the mean, class wise mean. So now let's say this is the class plus class mean, and this is the minus class mean. Okay, here also you can find out the minus class mean. Okay, here also the plus class mean. And then not only aligning the distribution marginally, conditionally also, like all the mean of the plus of the source domain should be aligned with the mean of the plus of the target domain. So let's say here the mean is there. Okay, so somehow you try to reduce this distance, mean wise distance. Okay, so now this is the distance you reduce, and you try to reduce. So here is the mean and here is the mean. You reduce this distance along with the classes. Okay, so then if you project the data, so definitely all the plus of the source domain and all the minus of the source and target domain, right, they will come close. Okay, so then definitely the situation which you are getting here, so will not arise. Okay, so then the performance of the model further can be improved. Okay, so now one question here you may ask, right? So what is the question? How you can, okay, for the source domain class mean you can find out, but as I'm saying to you, right, in the unsupervised domain adaptation approaches, you don't have the label information. If you don't have the label information, how you will recognize these samples are belong to the minus class and these samples belong to the target domain, this plus and minus? Could you find out the mean? Can anybody tell me? Could you find out the mean of the source domain mean? You can find out, right? Because source domain label information is available. But the target domain mean, can you find out the target domain mean? Yes or no? Any one of you? Just message if you yes or no. Can you find out the mean of the target domain without label? No. Anyone else? Yes or no? No, right? Definitely, because the label information is not given, because in order to find out the mean of the class wise mean, so definitely you have to correctly identify all the minus samples, right? If you want to find out the minus sample, right, so definitely you should know the label, then only you can find out the mean, right? If it is not given, then how you can find out, right? So that's why what basically they used, what they did in that particular paper. Okay, so in that particular paper, what they did, so there is a, like, this is the classifier. It may be support vector machine, or so what they did, so they are training the model by using the like source, access, and ys, source domain label. So labels are available. Okay, once the model is trained, okay, then they give xt, means target domain. Okay, if you test, so then it is going to predict basically the yt cap. So this is basically the pseudo label. They are not the actual label, right? But somehow because both the models somehow they are related, so the initial pseudo labels may not be fully correct, but somehow they are correct. Okay, with the help of this yt, so some pseudo labels, you can find out the mean of the minus class of the target domain and mean of the plus class of the target domain. So this you iterate like seven epoch or 8 epochs, or because as the distribution comes close, the generated pseudo label may be more and more accurate. Okay, so further you can apply here marginal distribution as well as the conditional distribution. Okay, so both the distribution basically you can perform. Okay, so with the help of this pseudo label concept. Now I hope this is clear. Okay, so now the second paper is I have discussed with you what was there, and another paper like correlation alignment. Correlation alignment means the second order movement matching. So second order movement matching you already know, right? So like the variance, second order movement matching is not the variance. So source domain covariance you find out, covariance of source and covariance of target. Okay, so this is the target domain. So then you align with respect, not with respect to the mean of the source and mean of the target. So full this covariance matrix of the source domain you compute, and the covariance of the target domain you compute, and then that distance basically you align. So that is basically the second order movement matching, and you can also call it as a covariance matching. Okay, so that is basically this correlation alignment method. So another method comes into the picture, joint geometrical and statistical alignment. So it uses both. I already explained you marginal distribution, conditional distribution, and this subspace alignment is almost similar to this correlation alignment. Okay, so that is also, so all three things together they are using. One more thing they are basically using, okay, the source domain discriminative information. Source domain is discriminative information means, right? So, you have a samples, right? So let's say the samples are like this, plus, 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 and the minus, 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 then plus come here, then plus come here, then minus will come here. This is itself in the source domain, right? So now you can see like in this space, so it is bit difficult to discriminate this kind of classes, right? So discriminative information means the minimize the distance between the similar class sample and maximize the distance between the dissimilar class sample. So if you project this data, right, because you know the label information, right? So definitely you would be knowing. So why not minimize the distance between all the similar class sample? So maybe you reduce the distance between similar class sample and extend the distance between the dissimilar class samples. So now see, after projecting in new space, you will see that the clusters are well separated. So distance between the different classes is increased and the distance between the similar classes is reduced. So they have done this technique also, source domain discriminative information preservation, that is done in this one. So then you see that the further the performance of the model was improved. Okay, so in order to preserve the source domain discriminative information, they consider linear discriminant analysis technique. You might have heard. So sometimes we call it as a Fisher discriminant analysis technique. Okay, so that technique was considered by them. Okay, so further to improve the performance of the model. Okay. Okay, so now this is done. So another one is the manifold embedding distribution alignment. So in this particular work, like this paper was proposed in introduced in 2018. So in this work, like source discriminative information and some manifold learning spaces, they projected some geodesic flow kernel space. Okay, and then they preserve the original similarity. This is new concept here. So what happened basically, the two samples. Okay, so let's say, so this is some similarity. They are bounded with some similarity. So when you are going to learn new space, it might be possible that they may go far apart. So let's say they have gone very far apart. So because of that, it might be possible that they may be misclassified. Okay, then preserving the original similarity. So you compute initially how much these samples are similar. Okay, so let's say some 0.2%, 0.9% similarity was there. Okay, once they have gone to some new space, now the similarity has got reduced to 0.2%. Okay, because of that, they are being misclassified. So what you can do, so further, whatever the similarity they had originally, again, when you are going to learn new space, so multiply by it. Okay, so they will be bounded. So again, they will come close. So because of that, it might be possible that they may not go far apart and they will not be misclassified. Okay, so this new concept they introduced, this manifold learning, some some well structured data they projected, and then they apply these two new contribution here. Okay, and then further I improved the JJSA method, just I had shown to you, right? So this kernelized unified framework for domain adaptation. So this work was proposed by me. Okay, so in this work, what I have done, so marginal distribution, like in the JJSA paper, like if I show you, so if I show you in the previous work, this JJSA, marginal distribution, marginal subspace, and these three means losses was there, right? These three objectives were there. So further, I have introduced one more objective, Laplacian regularization or original similarity. So that particular concept I had taken from this particular paper. So original similarity. Okay, so now I have come up with the new approaches, just incorporated one more objective, original similarity. So because of that, the performance of the model was improved, maybe by around like 5 to 6% over the like manifold embedding as well as the JGSA paper. Okay, so that was my newly contribution in this particular kernelized unified framework for domain adaptation. And another paper again further, though this is also linear discriminant analysis by pseudo label, this was also proposed by me. So in this work, I have found the limitation in my previous work, kernelized unified framework for domain adaptation. So in this particular work, so see, you were discriminating the samples of the source domain only, right? But what about the target domain? You are not considering the target domain, right? Because you also want, if the samples they belong to the same class, the distance of the target domain should also be reduced, right? And if they belong to the different class, that the distance between them should be more, right? Why you are not applying, right? So then what I have done in this work, I have extended this kernelized unified framework, right? So I preserved the source as well as the target domain discriminative information. Both I have done. Okay, so in this work you can see, so performance was greatly improved. So if I show you paper, let me just show you the paper. So all the papers are available in this PPT. One minute. Is my screen visible? Hello? Am I audible? Oh, okay, 1 minute. I hope it is now visible, right? Okay, so now this was my COFDA paper, right? So in that particular work, I have just, you know, so here you can see, okay. Sorry, this is the LDAPL paper. Okay, now here you can see this JJSA. Okay, so JJSA incorporated only like, source domain discriminative information, marginal and conditional distribution, and subspace alignment. Okay, so this is this JJSA paper. This particular. Okay, so then I proposed this LDAPL. So now how much performance you can see it got improved here. Okay, so for this is the Office Caltech data set. So like this is the Caltech, the data is collected. This is the Amazon from Amazon. Then Caltech site is there, and then webcam, right? One time this is the treated as a source and this is treated as a target. Then again, this is the Amazon website, it is taken and then tested on the Caltech. So different tasks basically are there. So you may go through this paper so you can also find out about all those work. Okay. So here also, like, see, I have also compared with the KUBTA, my previous method. Okay, JJSA, I incorporated the original similarity. Now you see it was 82 on an average, it was giving 82.6% accuracy. Now how much I got improved? So 86.83% improvement. Okay, so further, like LDPL I have proposed. So now you can see again 3% improvement I have got it here. Okay, so similarly for all the tasks you can go through it. Like I have tested on like many data sets. So I think all the data sets are shared with you, like this Office Caltech data set with surf feature and decaf. This is basically the some ResNet models are applied for extracting the features. This is some VGG models are applied for extracting this Office Caltech features. This is the coil dataset, and this is the MNIST and USPS dataset. Different agencies, they collected the dataset, some digit dataset, and this is the pi dataset, right? So on all those datasets I have conducted, and I have also performed some evaluation study that incorporated objectives are like good. And this is the representation after performing, all the approaches, how our approaches are getting good clusters as compared to the previous one. This is the original representation. This is the representation of the JJSA, and this is the representations of our method. Okay, both the source and target domain clusters we are getting in this one. Okay, so this paper is already attached here, so you may go through it more. Okay, so now this LDAPL is also I have reduced. Okay, now coming to the these approaches are like, I told, right, shallow domain adaptation approaches. Okay, so now I am going to discuss with you the deep domain adaptation approaches. Okay, so similar kind of loss functions they have also considered. Only the difference is that here, like manual, like feature engineering was done by some manual person, but here the feature engineering is being done manually, means automatically. So there is no one between your data and your model. Automatically the features are being learned. Okay, so here this is the first paper of deep domain adaptation. Okay, so it was introduced in 2014. Okay, so it considered just the source classification loss. Okay, so source classification, maybe the cross entropy loss function was considered. Okay, along with this marginal distribution. So marginal distribution means what I told to you, right? So mean of the source domain, mean of the source domain, and mean of the target domain. You try to find out and reduce the distance. Okay, so that's why here maximum mean discrepancy means mean of the source domain and mean of the target domain. You try to find out and reduce the distance. So that is basically the first paper. Okay, so then further, like this deep domain adaptation network, what they did, this source classification using the softmax, so same cross entropy and multi-kernel. So in this particular paper, there was only one adaptation layer where you were reducing the distance between the source and target domain. But here multiple MMD means multiple MMD you are applying on different layer of your neural network model. Okay, so that I am going to just tell to you. Just wait for a minute. So another work is, domain adversarial training network. Okay, so here they further consider the cross entropy loss function and then adversarial training. So as I discussed with you in the last class, right? So when I taught to you generative adversarial neural network. So at that time I told, right, so here they are just considering the adversarial learning to discriminate the source and the target domain. Okay, so further this deep coral. So coral method you have seen. Coral method I told, right? So you covariance of the source domain, like XS minus covariance of the XT target domain, you try to find out and you reduce the distance between them. Okay, so this is basically the statistical learning, coral. Okay, what they have done, same loss function they have applied, but instead of taking the feature directly from the image, you are taking some neural network model. So source and target domain you are feeding in some neural network model, and then you are computing these covariance matrices, and then you are reducing. So with the help of this one, you are training the neural network model. Okay, further, like this deep subdomain adaptation network for image classification. So they have considered the marginal as well as the conditional distribution. Okay, apart from the source classification loss, the mean of the class wise mean plus source, mean target minus, plus, so you reduce plus mean minus of source minus mean target minus. Okay, so local means like class wise also you are trying to reduce the distribution. So all the models like statistical, they were proposed first, but just a way of extracting the features. They are dealing with the direct feature. But in the case of these models, right? So they were taking the data with the help of the neural network model, and then they were using this local LMMD particular loss function. Okay. Okay, so there is a one more joint domain discriminative loss function. So in this one, I already told you, right? This coral loss function means covariance matrix, right? So distance between the covariance of the source and the target domain you are going to reduce. Source domain discriminative information means like they have proposed their own some instance-based discriminative information. Instance-based means the distance between the similar sample of the source domain should be less, and the distance between the different samples must be more. Okay, so then they introduced like JDDA in 2018, this particular paper. Okay, so far, like this is the second order movement matching, and first order movement matching means this marginal distribution. Okay, so further they extended this work. Okay, then they considered like source classification softmax function, and then higher order. So far you have considered first order movement means mean, and second order movement means covariance you usually call, right? But you can take the higher order movement matching also, like 3, 4, 5. Okay, so they see that if you go for this higher movement also, the performance of the model can also be improved. Okay, so then again this particular work was done by us. So in this particular work, what we did, so source classification loss, right, using the cross entropy, then local LMD and the coral loss along with the entropy minimization. All these losses together we have, developed the new loss function, right? Usually I told, right, so simple loss function, usually you use the cross entropy function. But these losses, if you incorporate it in a unified framework, so we have seen that, the performance of the model significantly improved. Okay, so now one by one, I'm just going to, I have taken their architecture and I'm going to tell to you about each and every model. Okay, so this is the deep domain confusion. So in this particular work, I told, right, so and apart from the cross entropy loss function, one more loss functions you have considered. What was that loss function? First order movement matching or maximum mean discrepancy. So here you can see, so initial data will look like this, right? This is the source domain data and this is the target domain data, as I have already discussed with you, right? So if you, because you, since you know the source domain level data, so you easily you can draw the decision boundary. But what about the target domain? So here you can see some of the samples, like they are still being misclassified here, like these samples are being misclassified, okay, by using the source domain classifier model decision boundary. Okay, so domain adaptation approaches basically try to project in such a space where all the samples of the same class they come close, right, and different classes they go far apart. So irrespective of the source and target domain. So that basically you try to do. Okay, so here you usually use the classification laws like cross entropy you have seen, because label information of the source domain is available. So with the help of this one, you can train the model. Okay, apart from these things, so you are using the MMD laws. So MMD laws means first order movement matching. Then here you can see this equation. Look at this particular equation. So this equation is nothing but a what? Mean of the source sample. And this is nothing but a mean of the target samples. Then you are trying to reduce this thing. Okay, so one more loss you have added. So this method is basically the deep domain confusion. So it was introduced in 2014. Okay, so now you can see the label images you are giving. So they are tightly bound. Okay, so this is neural network model. So they are basically the tightly bound, and unlabeled images also you are giving. Okay, so now you are extracting the features from here. Okay, and then classifier you are adding it here, and then the prediction like that particular source domain you are predicting some labels here. Okay, and so this is the overall law, means the architecture. So this is the your CNN model where you are feeding both label as well as the unlabeled data. You are extracting the data, and then the classification loss, and then the features, adopted features you are taking from the FC7 fully connected 7 layer, and then you are feeding them here MMD loss, and then again the classification layer you are going to build, and then you are giving it to the classifier loss. Okay. Okay, now deep adaptation network. So in this particular loss, so almost everything is same. Okay, whatever you have seen. Only, so in the previous case, if you see, right, so only adopting on the last bottom layer, only you were performing this adaptation. You are applying this MMD only on the last layer. But in between also, you can apply, here also you can apply the MMD. Here also you can apply the MMD. So that is nothing but a multi-kernel. Okay, so that was the work was done in the next paper. So in this particular work, so here you can see this is a one layer, a fully connected layer. This is the convolution output fully connected. So in between, you are trying to find out, we are trying to apply this multi-kernel MMD for the better performance. So somehow the performance of the model was improved. Okay, so this is the domain adversarial, right? So usually simple classification model. So basically input image you give. So this is the feature extractor, right? Features are extracted, and then it is given to the some classifier. Okay, so some simple classifier is there. So that usually you have been doing. In addition to this classification, you have added also one more loss. So this is the class classification. So one more loss you have added. This is basically the domain classification. Okay, so whether it is coming from source domain, whether it is coming the target domain, right? So it basically discriminated, and whatever the loss is coming, so that would also be back propagated. So that is done in the this particular domain adversarial training network. Okay, so just they have considered some adversarial loss. So this is basically the adversarial loss apart from the classification loss in this particular bus. Okay, so deep coral, right? I told in the deep coral, basically second order movement matching, the covariance of the source domain, right? So these are all the layers are there. So FC fully corrected layer, the covariance, you take the features and you try to find out the covariance of the features you have extracted from here, and then minus covariance of the features you have extracted from here. Okay, and then you reduce the distance. So one classification loss is there apart from one more loss you are adding. So that is basically the deep coral. Okay. Okay, deep subdomain adaptation. So in this part, deep subdomain adaptation, basically what you are trying to do. So earlier you have seen, right? So mean of the source and the mean of the target you are classifying. But here the mean of the class-wise mean. So this is basically the class-wise mean of the source and class-wise mean of the target class, right? You are trying to find out and reducing the distance. Okay, so what is the meaning? So mean of the source of the plus class minus mean of the target of the plus class, then you are trying to find out the distance, and similarly mean of the minus class of the source class and mean of the target of the minus of the target class. So that distance basically you are trying to reduce here. Okay, so that this is basically the classification loss, and this is your this is a class wise or conditional or LMMD, local mean maximum discrepancy. So that particular loss you are trying to reduce it here. Okay. Okay, so now coming to the joint domain alignment, JDDA. So JDDA basically I told, right, three things basically it consider. So one is the simple classification classifier, then the choral loss, second order movement matching, and then instance weight discriminative, right? So this is the choral and this is the distance, means the distance between the similar class should be less and the distance between the different class should be more. So these three losses together it has added this LDA, LDDA. Okay. Okay. So now this particular work was done by us. So here what we have done. Okay. So here we have considered the LMMD loss and the choral loss, and one more loss is this is a simple cross entropy loss, and this particular is the mean entropy, minimizing the entropy loss. These four losses together we proposed the algorithm. Okay, and this work pattern analysis PAA. Okay, so this work was published in the PAA I think 2 years ago. So this was our novel contribution. Okay, so this is the way, like I told, right? So either you can come up with a good combination of the loss function, okay, and also some architectures, some the feature extraction models architectures also you can modify. That contribution also can be done here. Okay, so now to show the effectiveness of all the algorithm, like existing algorithm and our algorithm, so what we have done, so we have considered some remote sensing data set. So these are the 4 data set time being I have just considered, and yesterday only for 2 days I have been running the experiment for today's presentation. So these are the 4 known remote sensing data sets. Okay, so first data set is UC Merced land use dataset. So sometimes we call it as a MC Merced dataset, and the UC Merced dataset includes 21 land use classes, each containing 100 images and captured at 30 centimeter resolution. Okay, and another one is the AID dataset, comprises aerial image from 30 different land use categories with a varying number of images per category, ranging from 220 to 420. So these many images are there. Then NWPU, this data set includes 45 scene classes with 700 images per class captured from various remote sensing platform. Okay, so then another one is the RSS and CN dataset, contains images from 7 scene categories with 400 images per category taken under different weather condition and scenes. Okay, so these are the some samples of all the data sets which I have just described with you. So this is the NWPU data set. This is the RSSCN7 data set. This is the MC. These are the samples like column wise. So MC Merced data set, and this is the AID data set. Okay, so now let us consider this AID and UCM data set. So now these are the classes basically available. So some, because it though it contains many classes, so some common classes we have taken, okay, which are common in both the data set. So you can see this AID data set. So baseball, beach, denser residential, dense residential, forest, medium residential, parking, river, sparse residential. So these are the 7 classes, and the 7 classes of, you can see this AID dataset and the UCM dataset. So these common 7 classes we have taken, and at a time, because since definitely the resolution, okay, and the quality of both the dataset will be different, right? 1 minute. हाँ हेलो, क्लास चल रही है. Okay, so at a time, I am going to consider this AID data set as a source and this UCM data target. And next iteration, I can consider it as a source and then next as a target. So as you know, so in answer, these kind of like 2 tasks you can construct here. Okay, so source you already know, right? So if you take the source usually has the label. So when you are going to train the model, so you will take these images along with their label. Okay, similarly, when you take these classes for the target domain, so you don't consider the classes. Okay, so this is basically the AID and UCM dataset. Okay, so if you see the samples of these images, how they are different, so that I have also illustrated here. So this is basically the AID dataset and this is the UCM dataset. So this is the river class. So could you see how much the difference in both the images, right? So the quality as well as the way of they have the data they have collected from different places, both are different, but both are representing the river. Okay, so the like like geographical wise, right, quality wise, illumination wise, both are different. Okay, the water quality also, color you can also see, the land color also you can see, totally different. It seems like it is taken from this images is UCM images is taken from some forest area, right? So both are the different. So how much the variability is there in both the even though they are from the river category, right? So now the baseball field also, you can see the UCM baseball field is totally different from the baseball field of the AID dataset. Okay, so this variability is there. So again, one more dataset like DDC, NWPU and RSSC and dataset we have taken. So here 6 classes are there which are common. Okay, so these are the 6 classes like forest, grass, industry, parking, resident and river. So similar classes I have taken from the target domain as well. Okay, so now here you can see how, like, again I have taken the river here. So how they are different, right? So here the river you see NWPU dataset, it is totally different from the RSSN CN dataset. So this is also one river. Okay, so then you can understand like how much there is a distribution gap between the source images as well as the target images here. Okay. Okay, now first I have implemented the model. Okay, so what I have done so far, if you have any questions, so feel free to ask me. Then I'm going to implement now. Implementation phase I am going. If you have any question, please ask me. You have any questions? Okay, I think you don't have any question. Okay. Okay, so here, see, I have taken this as a source, this river class as a source of this RSS CN as a source, and then I have considered this as a, sorry, this I have taken as a source, and this I have taken as a target. Okay, so these images you have given, this is a source images, along with the labels you have given to this convolution model. So this neural network model contains 3 convolution layer and 2 fully connected layer and 1 bottom neck layer. Okay, so definitely if you pass, so then you will get the learned feature. This is basically the extracted feature. Okay, then pseudo level also you may get it. Okay, so similarly, if you give the target domain, because you need not to give the label data, you just feed to only the source target features only, target images. If you give, so definitely this will you will get. So then also you can apply some classifier and you can generate some pseudo label as well. Okay, so now by using this label, you can construct the softmax loss or some cross entropy loss function. And then with the help of this cross entropy, you can train these models are same basically, one common model. So they are tightly bound. Okay, so same parameters are there. So with the help of this cross entropy loss function, right? So you can train the parameters of this fully collected layer and convolution neural network model. Once you train all the parameters of this model, right? So then you evaluate it. So when you evaluate, how you can evaluate? So you feed it, so generated some pseudo labels will be generated by the model, and you compare with the original label, right? And then you can find the accuracy, because this has been source images you have taken from the, while training the model, source images you have trained, right, from this particular river, right? If you test on this kind of, so definitely the accuracy will be poor. Then what you will do? What is the suggestion? So apart from this classification loss, you add one more losses, like as I already discussed with you, like first order movement matching, maximum mean discrepancy, second order movement matching, choral loss, right? So those losses you can add. So now next one, what I have done. So now see, if I have done this thing in the first epoch, you check it here, how much loss was there? 0.433, and test accuracy was 73.40. Okay, after 20 epoch, right, now you can see the loss is reduced to 0.0012, and the accuracy improved to 70 after learning the model. Okay, so now 78 point, this simple. Here you have not, this is a very, just here you have not adopted any domain adaptation concept so far. Just simply you are training the model from source images and just testing on the reverse images. Nothing you have done. Okay. In the next, so next work, this is the deep domain confusion, right? So in this particular work, what we did, so apart from this classification loss, one more losses you have added. So now in order to compute this MMT, you have to find out the mean of the source and mean of the target, and then reduce the distance. So some losses will come, and then these losses will be added with the classification loss, and then you back propagate it, and then learn the parameters of this convolution layer and the fully connected layer. So that you do. So if you do this thing, and then you test on the river data set. So now you will see earlier, so 78% something accuracy was coming. So initial beginning itself, here you might have seen, so loss was like a 0.4 something. So because of adding this contribution of this MMD loss, now loss increased to the 0.71, and the accuracy in the beginning itself 74.63. After the 20 epochs, now loss got decreased to the 0.31, and the accuracy 1% something improved here for this particular case. Okay, so now next one, deep coral. So deep coral I told, right? So what basically you try to do in the deep coral, you find out the, what basically you try to find out? Deep coral, what you try to find out? Can anybody tell me what you try to do in the coral? What you try to do in the coral? Can anybody tell me? Hello, am I audible? Yes, covariance means covariance. We find out the covariance, of the source domain and the covariance of the target domain. You basically try to find out and reduce the distance, right? So yes, second order movement matching, very good. Okay, So in this work, so in this particular work, so the covariance of, like, you extract this is the extracted features, this is the original, right? The convoluted features, and that's the convoluted features. Then the covariance of x dash s, and then minus covariance of x t dash, you try to find out, okay, and then reduce the distance. Okay, so if you do this thing, right, so you can see that how much improvement is there. Okay, so that particular thing you have done. So I think this is wrong. Somehow I actually, let me check. That much accuracy you may never get. Okay, so basically you try to do in this covariance here. Okay, so now next one is this is the JDDA. So here softness loss, classification loss plus choral loss along with the discriminative loss you have added. So these two more losses you have added here. Okay, so in the JDDA paper, and this deep here discriminative loss as well as this sorry, here discriminative loss they didn't add, just deep choral they have added. Okay, so this is just wrong, it is there. So here they have added some deep choral, means LMMMD. Okay, okay, so now let us see the summary here. Okay, so now you can see this is the baseline, then how much loss was there in the beginning, like for first epoch 0.433, and the accuracy was, you can see 78.33. Okay, TDC here just MMD you have used, so somehow like 1% something improved, and the loss also, like, how much it got increased. So here D choral, so somehow the loss is little bit decreased, and the accuracy is also very narrowly it has been increased. So here a covariance matching you have used. JDDA, so you can see the loss, like, slightly improved in the first epoch, and the accuracy is also improved to 81.33. So DSAN, so here LMMD basically you used, right? So now you can see the accuracy like improved to, just class wise if you try to reduce the distance, so the accuracy improved to 85.25%. Okay, so similarly SACAEM, so this is also our approach. So in this particular approach I told, right, entropy, okay, plus LMMD, okay, and plus choral, so and plus classifications, 4 losses together we have added. This is the first epoch loss function, and then we got 84, so slightly it has reduced. So because why it has reduced, so you have to appropriately fine tune the parameter. Okay, so it is not necessary if you keep on adding, for some task it may give you the good result, for some task also it may not give you. So some objective may work as a redundant. Okay, but overall performance we will check, so somehow this SSCEM will perform good. Okay, so this is the basically the summary of comparison of all the algorithm. Similarly, so one more data set we have considered. So this data set basically was collected by us. Okay, so underwater object recognition data set. So underwater animal. Okay, so this data set contains around like 30 classes. So like jellyfish, all those classes we considered. So this is the original like we collected, and this is the images we have taken like from, you as you know, right? So collecting the original images in the underwater or sea, it is very difficult, right? You cannot get the data as you can get in the physical world. So you may not be, because you have to go inside, so inside the water, and you have to find the all the objects or species, and then you collect the data. It is not easy inside the water, but at the same time you may have some scratch printing. A lot of data is available in the internet. Okay, so by using this internet data you can train the model, and then you can test on the original data. So this is also one real application of underwater object recognition. Okay, so this is the work basically we submitted in the Ministry of Earth Science, and they also funded us one project to carry on this particular project. So these are the classes. So basically 30 classes are there. So like angelfish, betta fish, fox fish, clownfish, crocodile, dolphin, dory, right? Electrical eel. Okay, so these are the basically the 30 classes. Total 30 classes are there. So these we have taken some images from the underwater as well as the we have taken from the internet as well, with some painting, scratch, some those images. Okay, so now again we have tested on all these algorithms, right? So baseline algorithm, original data we have taken as a source, and the painting we have considered as a target. So baseline without domain adaptation, we are getting 84.10% accuracy on test data, is painting data. And when you apply the DDC means first order movement matching, means maximum mean discrepancy. So somehow like 80.80% improvement is there. When you apply the decoral, so now you can see 86.50% improvement you got. When you apply the JDDA, so 85.5% improvement you got. Okay, and then DSN means here LMMD just you applied, right? So 87.60. But you see here SACEM. So this is a combination of LMMD, entropy, plus coral and is classification loss. So now see, compared to all previous method, so now it has got like 2-3% improvement something. Okay, so similarly I can take a one more task as a P as a source and the for painting as a source and the original as a target. Okay, so this is the one. So now what is basically happening? So some like 10 classes out of 30 classes I have taken. So I have tried to visualize it. So painting images like, original to painting. So you can see here. So this is the initial representation, how the data is looking. So 10 classes, source and target, like, circle is representing the source and the triangle is representing the target. Okay. After performing our domain adaptation, how well clusters you have got it here. So easily you can identify the samples here, right? So this is happening after the domain adaptation, after like applying our approaches. Okay, so these are the references. Okay, so if you would like to, as I told, right? So if you would like to access, the papers are already there. So all the papers, whatever I have referred here, so you may go through those papers. Okay, so all like this paper like SACEM, so pattern analysis and applications, you can find it out. Okay, so here also you can see I have compared it, we have compared with all the existing algorithm like simply ResNet model, all those models, different conventional method as well, GFK, Coral, this is the method. So you may go through this paper. So similarly, JJSA papers, you can also go through it. And all the papers, whatever we have, I have presented to you, all the papers are available. Okay, now coming to the coding. Is my screen visible? Can you see the code? Yes, okay. Okay, fine. So basically, we have implemented this code on our, like, GPU, right? So our college AICT means academic GPU. So as usual, I'm going to just run. So with the help of, you can see the configuration of the GPU, like 40 GB data means GB available. So out of this GP, we have used means our model is going to use that particular that much memory. Okay, and some, like, if existing algorithms are running, then we can kill it. So here you can see now it is completely free. Okay, now no algorithm is running. So that much space is given. So if any warning will come, so I have reduced. So all these libraries you are already familiar. We have already taught you in our previous session. So different Taurus Vision library, data loader, okay, all those libraries. And this is for if you have the GPU, right? So you can run your model on GPU. So since in this particular data set, you have total 30 classes. So, and batch size, 30 classes are there. Batch size is 64 and 20 epochs you are taking. And the some parameters value, you can choose any one of them. So animal, so you are taking source trend loader, animal original data you are considering as the original. And this animal P you are considering as a painting images. Okay, so other data sets are also there, like I told, right? AID, UCM, the NWPU, RCN. So those data set also you can use. Okay, time being, I am using the animal data set. So trend loader, like converting your old data into the batches, like trainable format, like batch wise, you can take the data. And this is basically the implementation of HOM, is higher order movement matching. So first order you have seen, second order you have seen, right? So this is the instance-based discriminative loss function. So I talked about, right? So the distance between the similar class should be less, and the distance between the dissimilar class should be more. So for that particular criteria, you can use this instance-based discriminative loss. This is the implementation of the discriminative loss. And this is the MMD loss linear function. MMD means maximum mean discrepancy. Mean you try to find, you can see we are trying to find out the mean of the source and target domain, and we are trying to reduce the distance. This is the local MMD, means class-wise mean of the source you will find, class-wise mean of the target you will find, and then you reduce the distance. आदित्य सर, अभी टॉक चल रहा है सर. हाँ हाँ, ठीक है, ठीक ठीक है, ठीक. The LMMD, and this is, I told, right, choral loss. So this is basically the, you can see this is the covariance of the source domain, covariance of the target domain you are finding. Okay, and this is the Gaussian kernel, polynomial kernel. MMD loss could be mean could be of three types. You can take, or either you can take polynomial, you can take Gaussian, you can take linear also. And this is your entropy loss, as I told to you. And this is also one contrastive loss. So this is the functionality of the contrastive loss, is also similar to the instance-based discriminative loss. And one more functions we have added, like, if you are going to implement adversarial loss, right? So I told adversarial loss to discriminate the sample is coming from which domain, source domain or target domain. For that particular, I have defined a one particular class here to discriminate whether it is from the source domain and target domain. And this is the basically the adaptation model. Adaptation model means, like, some pre-existing pre-trained model you are using, right? So definitely the pre-trained model, if you are using, so let's say ImageNet dataset, it has been trained from the ImageNet dataset, right? So then out an ImageNet dataset contains how many classes? Around 1000 classes. Okay, so definitely the output layer would be having the 1000 as an output. But in the when I taught you the transfer learning, transfer learning concept in that particular lecture session, I told you that the output layer you have to modify as per your available number of classes. Okay, so that's why this is the open adaptation. So since in our data set, how many classes are there? 30 classes are there. Okay, so that's why the last layer, classification layer. Okay, so as per our requirement, as per our number of available classes, so you are going to take it. Okay, so this is the adaptation. So you may go through it also. And then this is the feature extractor. So here feature extractor means like, you have because here we are considering the pre-trained model. So you can see loading a model.vit v16. Okay, and then this is the model, and then the last layer you are modifying it as per the number of classes. So definitely it also might be having the 1000 classes. So now you are converting it to the 30 only. Okay, so this particular class is also there. Now one model like VIT extractor, now model you have created, and then you have model pushed to the our GPU. Then this is the cross entropy loss function, simple instances you have created. And then this is our domain adaptation, like last layer, it was having like pre-trained model was having 1000 classes. Now you have converted into the, हाँ सर मैं क्लास में हूँ, मैं करता हूँ आपको. Then this is the as usual, right? So when you are going to develop the model, so usually you have three parameters, right? Three things. One, model definition, means loss, and then optimizer. So what parameters you would like to optimize? The model parameter. So this is your model you have created, and this particular model you have taken VIT vision transformer model, and the last layer you have modified, right, with your number of classes, means 30 classes. That particular model you are giving to this stochastic gradient descent optimizer, right? And then in each epochs, like 20 epochs are there. So training loss in each epoch, test loss, train accuracy, test accuracy, you are going to store on these particular parameters. Okay, so like as usually like model.train. So now your model will come into the training phase, right? So then batch wise also, epoch wise also, how much accuracy and losses are there, right? You are also going to store it here. Then when you are going to source trend loader, right? So since your whole data you have divided into the multiple batches. Okay, so one batch in each epoch you can extract it. So now some batch of samples have come from source as well as the label. Now you have pushed them onto your GPU. And then at the same time, the target domain you are going to give it. So one batch of the target domain sample, only you see you are not extracting here. Here you are not extracting the target label. Here just you are extracting what? Just you are taking what you are just giving here. You are just giving just taking only the target sample, not label. Then again you have pushed them. Okay, then you are passing them through the model. So model is going to generate two things. One is the feature, and then those features you pass to the classifier and then corresponding labels. Similarly, you will do for the target domain as well. So now both you have generated over here. Okay, and then this is a target domain, converting in appropriate, like, some format, because here argmax, so some label you want, but it will give you in the form of one hot encoding. So proper label you want. So then label you are going to extract it here. So this is your simple classification loss. So this is the predicted loss, right? And this is your original loss, right? So then you can compute the classification accuracy. Okay, and then one more loss is there. This is the LMMD loss. MMD loss is also there, right? So I'm just going to enable all the losses. Okay, MMD loss, I told the mean of the source, the source features you are passing, mean of the target, and then when you are computing the distance between the source and target domain, mean, so which Gaussian you are using. Either you can use polynomial, linear, or Gaussian. Okay, so then it compute the difference between the mean of the source and the target domain. This is the MMD, maximum mean discrepancy. Then this is the choral loss. The covariance of the source features, covariance of the target will be find out. Then this is the instance-based discriminative loss. one more loss I told, right? So what is that loss? Basically, uh, instance-based discriminancy loss means the distance between the similar samples should be reduced and the distance between the dissimilar samples should be maximized. So this is basically the loss. Then the MMD loss. So four things you need, right? Because see, four things: the source features, target features, along with source actual labels, and then predicted labels also you are giving, right? Because you, for creating the mean of the target domain classes, you require the label information, right? For MMD, you don't require, but for local LMMD, you require. So that's why you are passing in this LMMD. So this is, you can also go through it. Okay, so now this LMMD you have computed, and then entropy of the target domain also you have computed. And right now I have disabled all the things, all the losses, except so you can also do this one thing. So I have disabled. Okay, just I am taking the cross entropy loss. So far I am not applying any deep domain adaptation approaches. Okay, then as usual, this is the like for if there is any gradient is there, so you will it will become 0 and then compute the gradient and then learn the parameter. So these three steps, and then these losses, whatever the loss is coming, and then the accuracy is coming, and then take the average of that particular batch. Okay, and then you take the average of that particular epoch. Okay, so this is the thing, like accuracy of the source domain you can compute. Then evaluating like the target domain, right? So you have to right now in the training phase is there, right? So gradient each and every time you are computing. So but at the time of testing you don't require the don't need the gradient. So you will come to this evolution mode, and then gradient don't require. Then you take the samples like batch wise from the source and target domain, and then you test the model evolution, and then here testing the means testing accuracy you are computing in this particular model. Okay, so now what I'm going to do, I'm just showing you. Okay, so now we will see, just wait for. Meanwhile, if you have any doubt, please feel free to ask me. See, now it has started. Okay, so this time what I have done, animal original as a source I have taken, and painting a target I have given. So now you can see just without domain adaptation how the performance of the model is coming. Okay, so now like you can see the accuracy has become saturated here, like 84% only. I don't think so it may improve from this 84% or 4%. Okay, so that is basically this uh, like you can see 84, like it will be saturated. So now let me stop it here, and then I will show you, like let's say if you use apart from this like some other loss, let's say LMMD loss you are using. So as I told, right, so you have to use some hyperparameter here. Otherwise, the impact, like the loss which you are computing is too much. Okay, so now you can see. So let me use. Now 84 was the accuracy after 7 epoch, 84. Now you will see around like, somehow 86, 87% you will see the accuracy after adopting this LMMD loss.